Perfect, thanks. How are you doing? First, just a recap on the calendar. You know that we didn't teach last week, so I updated on my website the calendar, and I take this opportunity to remind you that next Monday there will be no lectures because I think the reason is the degree day. There are degrees, and therefore we cannot teach that day. So next lecture will be in 2 weeks from now. And I updated the calendar also by removing the lecture that was planned last Monday. And therefore I added an additional, I extended my calendar to Monday, 27 April. So this means that my colleagues, which will teach the second part of the course, will start next Monday. And actually, I am also trying to make an effort to recover the lecture in a different date, but I still don't know when. Maybe that we can plan a lecture online, but in this case, I will consult with you just to make sure that my colleagues have enough time to complete the lectures by taking into account their commitment. I have no problem in teaching Monday, 27 April, but I need to check whether then the weeks that are left allow my colleague, because they have a different timing. I think yes, I think they have time, but I need to check with them. So for now, the moral of the story is that please keep this calendar as the current one for my part, and therefore let's assume that my colleague will start after I completed my part, okay? I need to check with them. Okay, and then I just would like to start from where we finished last time. You have the videos, by the way. And last time we talked about climate change in a more extended discussion, and then we completed the last lecture by discussing data, and in particular we discussed proxy data, tree rings, paleoclimatic reconstructions. What is the purpose of discussing data? Of course, our overall target is to understand the science of climate change and therefore to understand how we model it, because understanding the science gives the basis for us to model the climate system. And an essential part of modeling is input data, and therefore we started by discussing the data. Now we have to start discussing more in detail how the climate system works in order to get the basis for our understanding. Understanding is essential before modeling. In principle, you could use climate models even without understanding the science behind it, because there are a lot of softwares, and in general you can find nowadays, and this is a marked difference with respect to the past. Only 10 years ago we didn't have so many opportunities. You can find nowadays software for everything you need to do, and in particular for making predictions, modeling Earth system, environmental system, making prediction of meteorology other than the climate, making predictions of air quality. There are plenty of softwares which, can be broadly subdivided in two categories: open source and free software, and commercial softwares. And basically the difference between the two is not so easy to describe with few words, but if I had to identify the most striking difference, besides the price, which in some cases is a relevant difference because some commercial softwares are very costly, but another striking difference is the level of user friendliness. The commercial software basically has been created to support the use by many, because it is the purpose of the commercial activity to reach a lot of people. And therefore, they had a very good motivation to take our current level of knowledge, to take open software and make it accessible to a lot of users, which is also a commendable action, because indeed, if we want to be effective in reaching the users, and reaching the users is important because the users are policymakers, are administrators. In order to be effective, we have to make the users capable of using science, so using the software. And therefore, it is a commendable action that some people invest money in making the software accessible. And this is a striking difference, because in order to use an open software in general, we need a very good knowledge of coding, a very good knowledge of how the computers work. And this is why last time I told you, try to gain skills in computing, in the use of open source software, in the use of the PC in general, because it is, first of all, a distinguishing feature in your CV and gives to you the opportunity to make things that otherwise you wouldn't be able to do, or you would be able to do that only by spending a lot of money. So this is the reason why I encouraged you to make this effort. So in principle, and I go back to my original reasoning, you could use these softwares, either commercial or open, even by ignoring the science behind it. And this is what many administrators and policymakers do, because they don't have the basis and then don't have the time to understand the science. However, if you want to play the role of an expert, a researcher, a scientist, then you really need to know what is behind the software. So I encourage you to use the software because it saves time, and also in some of the cases it's practically impossible to set up independently a new software doing that. It's a teamwork, and some of the softwares that you can find open source on the web were created by international groups of distinguished people who dedicated their life, their career to that. So you have to use the software. But on the other hand, you have to know the science. Why? There are several reasons for that. First of all, if you want to communicate the results, you cannot simply say, I use that software and that's it. Because you have to explain, you have to gain the trust of the people you are talking to. And gaining the trust is essential in order to be effective, especially in climate. Because, you know, there is a lot of disinformation, a lot of denialism, which makes spreading the voice complicated. So if you know what is behind it, what you are presenting is much better. This is one of the first reasons, one of the reasons. Another reason is that the softwares, like humans, can be wrong, like artificial intelligence, the so-called artificial intelligence can be wrong. And how can we understand if a result is bugged, is wrong? Only by knowing the theory. If you know the theory, if you know the orders of magnitude, then you can spot out bugs in the softwares and you can correct the results. And this is essential if you are a specialist, if you are a scientist or researcher, to make a check. And this is why I invited you to get familiar with the orders of magnitude. There is a good advantage, a good feature, a nice feature of computational errors. Usually when they are wrong by a lot, like an order of magnitude. So instead of getting 10, you get 100, or you get 0.01. So on the one hand, this is concerning, because if a mistake is tiny, then you may say from an operational point of view, it's not a disaster. That's fine. So on the one hand, it's concerning. On the other hand, it is reassuring, because if you know the order of magnitude, then you can easily spot out the problem and you can resolve it. And I give you an example. If you set up a model for modeling the annual rainfall in Bologna, and you know that it's about 700 millimeters, because this is the value of the rainfall that we get here in 1 year, cumulative rainfall in 1 year. And I already mentioned this example, and on average, of course, then if you set up a model for modeling the annual rainfall and you get a value of 50 millimeters instead of 700, then you can realize that there is something wrong. Or if you get 7,000 1 year, you realize that there is something wrong. While if you set up a model and you get a rainfall of 600, yeah, that's fine. Let's try with another year, and then maybe you get 800. So the average is around the correct value. So this is why you have to become an expert of the order of magnitude, because the softwares, which I, again, encourage you to use, very frequently are wrong. There was, I'm not sure if there is still there, 10 years ago, a website describing the bugs of Excel. When you make a computation in Excel, you of course assume it's correct. 10 years ago, there was a website listing some trial computations that people could try in Excel, providing completely wrong results. And it was very interesting because it helped in understanding that even when you make a computation in Excel or with a pocket calculator, it's useful if you still have the power of making a mind calculation, because you can easily check. If you type 10,000 divided by 2 and you get 500, of course, mind calculation, very easy to do in this case, is 10,000 divided by 2 is 5,000, and you can check. But if you don't have this capability, because we tend to lose it, mind the computation, we tend to lose it because, of course, like we tend to use the capability of handwriting. When I try to handwrite today, really, it's very tiring for me. And sometimes I can't even myself read what I have written because we are not used to. But this is something that makes us, in terms of mind computation, makes us more vulnerable to errors, to mistakes. Just be aware of that. Okay, so understanding the science is important for this many reasons. So let's try to start discussing it. And let's go to our next link, the Earth system. Because when we describe climate, we describe a piece of the Earth system. Let me open the PowerPoint, which helps me to remind what I have to say, to remember what I have to say. And the PowerPoint is, as usual, down here. Okay. Okay, here it is. 1 second. Okay, good. And let me keep the website here because I also need some of the links. Okay, the Earth system. Good. So, the Earth system, what is the Earth system? We define the term Earth system, the group of the several processes governing the evolution of the Earth and its atmosphere. Okay. The Earth and its atmosphere. There are several processes which support, which govern the dynamic. Dynamic means as a response to driving forces and changes over time. There are several processes that drive the evolution of the Earth, intended as evolution of life, evolution of the several flows of matters that occur within the Earth system, and the evolution of the atmosphere. There are several processes, and I would like to start with this figure because it shows what I'm talking about, and it shows that it's a complicated system. Why it's a complicated system? Because it involves several processes. Think of the flow of energy, the flow of water, the flow of pollutants, of contaminants generated by humans, and think also of the human society. The evolution of the human society is governed by processes that are part of the Earth system. And these several processes are all interrelated to some extent. There are some links that are more powerful than others, other links that are less important, but still there are many and many links. Virtually, we can say that any subsystem we can think of in the Earth system is related to all the others. And these links are expressing two waves interactions. So there are indeed multiple connections. And of course, if we want to understand how an individual system evolves, then we have to consider how the other systems, how the other processes evolve. And therefore, we easily understand that we should understand and consequently model this complicated system as a whole by adopting what we call an holistic approach. Holistic is a buzzword today. It's a very popular term. What does it mean? That we have to take into account everything. Holistic means comprehensive. It's a technical term, so comprehensive is not a good synonym, but it means that we have to look at the big picture of everything is involved. So we have to consider the Earth system as a whole. But this makes understanding not easy, and also modeling is not easy. Because modeling all of these interactions, you understand, any link is an additional complexity. Any link in a mathematical model is an additional equation. Any link may introduce state variables. We will see what are the variables in a model and what is a state variable. And therefore, the number of equations into a mathematical model increases, because remember that any system introduces, any process introduces one or more unknowns, one or more variables that we have to describe, and any unknown means that we need an additional equation. Basically, these models that we try to better understand are systems of mathematical equations. It means that there are mathematical equations which we need to resolve all together. This is a system of equations. And we know from our already secondary school what is a system of equations. And we also know that the higher the number of equations and the higher the complexity. Okay? So in the traditional approach, we decided at the beginning to subdivide the Earth system into subsystems and analyze each of them individually, because this allows us to focus our attention. Which is a smart idea. It's a smart idea also for didactic purposes. Still, in fact, the subdivision in subsystems of the whole Earth system is very good for didactic purposes. So let's try to better understand how this subdivision was made. But let's first start from emphasizing once again, because we already discussed this, a distinguishing feature of the Earth system. The Earth system is a closed system. What does this mean, closed? And you can look over the web for the definition. A closed system doesn't exchange matters with the external space. The only thing that can be exchanged by a closed system is energy. And this is precisely the case for the Earth system. The Earth system is exchanging energy with the space. Think of the energy from the sun, but also the energy that is emitted by the Earth system into the space. We will discuss it. And then that's it. Given that there are no other exchanging of matters. With matters, we mean the mass, any kind of mass, like water, air, or whatever component, metals, whatever. There is only an exception for the Earth system to this situation, this state of closeness. What is the exception? Exception is given by bodies that can enter the Earth system from space, like meteorites. And in this case, there is indeed an exchange of mass. It's a mass that is received from space, or also when the comets enter into the Earth system, provided they can enter it indeed in the atmosphere or other bodies in general, there might be an exchange of mass. By the way, this impact of meteorites, we can neglect it for our purposes, because our purposes is to model the Earth system in the time span of a couple of 100 years, maybe. And this is a time scale that is negligible when compared with the time scale of the processes that may bring meteorites into the Earth system. Still, this phenomena occurs and are very frequent, but with frequency computed at the appropriate time scale. And actually, this phenomena, which we already discussed, can be potentially very impactful for the system, because sometimes these bodies are very large and then can change the inclination of the Earth's axis. They have the potential of changing the climate and the potential of triggering important other changes. But the time scale is very long, and it's unlikely that in 200 years we may experience such an impact, such a significant impact. Sometimes we experience impact that are not significant, it's small pieces of bodies. But a big one, which would bring a mass that is significant when compared to the mass of the Earth system, then it's very infrequent. But actually, if we look at the long time scale, and Mars is an excellent example, Mars is without atmosphere. And therefore, it means that once that the planet Mars is impacted by a meteorite and a crater is excavated by this impact, in absence of atmosphere, in absence of a water cycle, this crater remains there for billions of years. And in fact, we know that Mars has been without the atmosphere for already many billions of years. And the result is that if you look now at the surface of Mars, and we know it with very great detail because of the exploration that delivered through remote sensing, very detailed digital elevation models. And now we can see over Mars a multitude of craters, thousands of them, some of them very large, which means that indeed in few billions of years, which looks like a long time scale, but in the planetary time scale, few billions is a normal time scale. In few billions of years, also the Earth may receive a lot of these impacts. I'm sorry. So their system is closed. Now, let's go back to our reasoning. And if we want to divide the Earth system into subsystems, what approach could we take? And a traditional approach is to divide the Earth system in spheres. This is why, for instance, the atmosphere is called like that. Okay? Because a sphere means a domain of, in this case, atmospheric processes. And there is not only the atmosphere. So the atmosphere is one sphere of the Earth system, which we try to study and understand individually. In fact, if you look at the various branches working in geosciences, you find an important branch that is atmospheric sciences. That's it, because it is a branch of science that looks at the dynamics of the atmosphere. And here you see other examples. The geosphere is the domain of the geology, and therefore it is studying the plate tectonics, the evolution of the geology of the Earth. And then there is the biosphere, which is the sphere of the living organisms. So ecosystems and forests, humans. The hydrosphere is the sphere that describes the flow of water, flow and storage of water. It is the domain of the water cycle. And these are the main spheres which we can take into consideration. These were the first four, okay? Traditionally, we subdivided the Earth system in these four spheres. In my website, there is a link to Geoscience Videos, and Geoscience Videos is a nice website that I already mentioned to you for educational purposes. But I mean high-level education, like high school and university. And there is a video presenting the spheres. I'm not looking at it now because I am planning to look at another video just in a few minutes from now, and therefore I want to limit the number of videos that we see in the room. But on the other hand, if you are interested, this collection of videos given in Geoscience Videos is really interesting. There are videos describing the evolution of climate, the evolution of plate tectonics, etc. So these four spheres, you know, they are a very small number. So with the evolution of Earth system sciences, we identified additional spheres. And the cryosphere, describing the domain of snow and ice, the lithosphere, describing the domain of the land, lithology, okay? The pedosphere, describing the soils, and finally, the technosphere, also called anthroposphere. It's the sphere describing, studying the dynamics of processes that are related to humans and human impact then. And the technosphere is the last of the spheres that was introduced. And it was introduced, I would say, about 25 years ago, 25, 30 years ago, after we realized the increasing imprint of human activities on the dynamics of the Earth system. And it was the discussion that brought to the idea, that raised the idea of introducing a new era, and the Anthropocene. Geologic eras are identified by looking at geological signatures. And now we are in the Holocene, which is the last era. They usually have a duration that is much extended. And recently, in this discussion, it was questioned that the impact of humans already reached the level to mark some geological signatures. Therefore, marking the start of a new era, the Anthropocene. There is a long literature, if you Google for Anthropocene, a long literature. Paul Crutzen was the father of this idea, and he recently passed away. Still, the discussion is open. The discussion is open because the agreement was not reached about the already significant influence of human impact in terms of geological markers. So there are some people sustaining that it's a good idea to introduce this new era, other people who based on good motivations, point out that, decide whether it's the time to start a new era is a decision that is very important. But still, there is an agreement that humans today, and since about after the Second World War, are indeed playing an important role, also in climate. And therefore, this is why we introduced the technosphere. Very good. So these are the various spheres, which are, once again, all connected each other with two-way interactions. So how can we describe these spheres and interactions then? How can we, in a manageable way, to understand how these interactions are driven and how they evolve? So a way to look at the connections between the spheres may be to concentrate on the flow of matter, on the exchanges of matter and also energy among these spheres. This can be a way to understand the links, because the idea is, once again, that of splitting a complex system of interactions into categories so that we can focus individually to each one of these categories. So let me just give you an example. An example is, for instance, to look, as I said, exchange of matter, and then to look at carbon. Carbon is passing from one sphere to the other. Carbon is in the atmosphere, we know, because CO2 is an important greenhouse gas. Carbon is in the ocean, we know ocean acidification and the various problems. And carbon is in the soil, we know that fossil fuels are storage of carbon. And therefore, by looking at the fluxes of carbon, because carbon moves from fossil fuels to the atmosphere while we burn these fossil fuels, and this is something that humans do. So it's involved the technosphere or anthroposphere. And then carbon, through precipitation, reaches back the land. It's absorbed by vegetation, absorbed by oceans. So if we look at the carbon cycle, then it's a very good way of understanding some of these interactions. They are not all, but they are important interactions. This is an important part of these links. And why it's important? Because carbon, we know that is regulating the exchanges of CO2, is regulating the concentration of CO2 in the atmosphere, is regulating the ocean acidification. So studying indeed the dynamics of carbon is essential. Today there is a lot of research activity trying to better quantify the carbon cycle, because it's not easy to model the carbon cycle at the global level. And we have estimates of these fluxes, rough estimates, like we have estimates of the human emissions. But these estimates are still uncertain, and it's still uncertain what is the reaction of the various spheres to the increase of carbon or concentration of CO2 in the atmosphere. We know some of the effects, like global warming, but still we don't know what is the reaction, for instance, of vegetation. So vegetation with more carbon in the atmosphere, carbon is a fertilizer, so the vegetation can absorb the carbon and then grow more, and this is a reaction of the biosphere. And we still don't know what is, in quantitative terms, the effect, the mitigation of effect by the vegetation to mitigation of increased atmospheric concentration of CO2. So the carbon cycle is a very active field of research, which is very related to climate change. And here I have a figure of the carbon cycle. But before introducing it, I think there is a nice video of the NOAA, the National Oceanic and Atmospheric Administration of the United States, which I think we can have a look. It's just a few minutes. I am setting it to velocity of 1.5 because it's still understandable, and I don't want to take much of your time, but I think it is interesting. And the link is in my website, and let me see, it's here. So let me just set it to, let me stop it 1 second. Okay. Good. Okay, it's 1 minute 25, so I think we can look at it in normal speed, but let me just check why we don't have any sound here. One second, otherwise, if I'm not able to resolve quickly, I can defer it to you. Okay, here. So let's see. No, there is no way, just 1 second. Chrome. Okay, let's see if there is the text in there. Not exactly. Okay, let's forget about it. Anyway, you have the link, so you can refer to the link, and if you are interested, my suggestion is to have a look at it. And just 1 second, I want to. Okay, good. Let me see. Yeah. Okay, let's go back to our figure. Here it is. So here you see some pictorial representation of the carbon cycle. Carbon cycle, which is essentially an exchange of matters between different processes, matter which is carbon, between different processes within the Earth system. And this exchange, this flow of matter, is fueled by the energy of the sun. As any flow of matter in the Earth system, we know that the only energy source in the Earth system is given by the sun. So we have the energy of sun that basically stimulates the growth of vegetation, and therefore this growth of vegetation causes a carbon storage into vegetation. The carbon storage is also called, especially in climate science, carbon sink, which means an absorber of carbon, which is particularly important because carbon sinks contribute to the reduction of the CO2 concentration in the atmosphere. And then this part of this carbon is stored into the soil in the form of fossil fuels, which are originated by the degradation of dead organic matter. So vegetation, once that reaches the end of its life, then it is decomposed over the soil and then included in geologic times into the subsurface in the form of fossil fuels. Can be coal, can be oil, etc. And then we extract these fossil fuels and in the form of petroleum, coal, natural gas also. And when we burn the fossil fuels, we basically give back to the atmosphere the carbon, and therefore the storage is the storage of carbon in the solid earth is decreased for the impact of human activity. And then part of this carbon released to the atmosphere is stored into the oceans, because the ocean is another very relevant carbon sink. And in particular, when the temperature of the ocean decreases, then it is increased the amount of carbon that is stored, can be stored by the ocean. And then there is, of course, the contribute of transportation, releasing emissions of CO2. And then there is the storage in the atmosphere, which increases the concentration of CO2. From this picture, it looks like only human activity is regulating the exchanges. Actually, the carbon cycle existed well before humans, and therefore there is a continuous exchange, natural exchange of carbon, because even if we don't extract fossil fuels, you can think, for instance, of the oceans. When there is an increase of temperature, then the oceans release CO2. So there is a continuous exchange of carbon between the oceans and the atmosphere. And the volume of carbon that is involved in these exchanges is very large. And the burn of the fossil fuels can also happen for natural causes, because during fires, which are typically induced by thunders or by natural causes, through fires, there is also an exchange, a release of CO2 in the atmosphere. There is vegetation that is burnt, and then a release in the atmosphere. Of course, the human activity amplifies, accelerates the carbon cycle. Acceleration means that we accelerate the release in the atmosphere, but then it's also accelerated the exchange from an atmosphere that is richer of CO2. There is an acceleration of the exchange with the vegetation, and therefore, because CO2 is a fertilizer, and an acceleration of the exchange with the ocean, and in fact, ocean acidification is increasing. And the fact that the carbon cycle is natural cycle can be realized if we look at the dynamics of carbon concentration, the progress of carbon concentration in the atmosphere, which we reconstructed from paleoclimatic data. And therefore, we know that the current concentration of CO2 in the atmosphere is the larger in the past 500,000 years. So the Earth system in the past 500,000 years never experienced a so large concentration in the atmosphere. But if we look far back in the past, and now we can reconstruct the temperature and therefore the CO2 concentration far back in time for more than 3 billion years, we realized that in the past there were in the atmosphere of the Earth concentration of CO2 that were much larger than today. And in fact, we had very warm periods without the ice caps. And the reasons for these big changes, natural changes, are not known, but it could have been volcanic eruptions, because I forgot to mention volcanic eruptions trigger also exchanges of carbon from the solid Earth to the atmosphere, and also they trigger fires, and therefore, indeed, the reason could have been gigantic volcanic eruptions, whereby what are called mega volcanoes. Mega volcanoes means that we know that there is the potential for volcanic eruptions that reach an extension with the magma to cover a continent like the whole Italy and a large part of Europe. There are some mega volcanoes that are known that have the potential of triggering such radical changes in relatively short times. And so this could have been a cause for these changes in climate or the impact of meteorites. And therefore, we know that this exchange of carbon has been always active, and with behaviors that were completely different in the past. And this is something that we are trying to understand in order to assess to what extent the human activity is influential relatively to other causes that could alter the concentration of carbon in the atmosphere and in the other parts of the Earth system. But anyway, the moral of the whole story is that if we look at the carbon cycle, this could be a way to understand the links between the spheres. What are other possible links to be investigated? Let's look at another important cycle, which is the water cycle. The water cycle is governing the exchange of water and the flow of water within the several parts of the Earth system. I don't spend much time because we know the water cycle since the primary school, and we all have a quite good general knowledge of it, how it works. Again, it is fueled by the energy of the sun. And we know, in broad terms, we know quite in detail how the water cycle is impacted by humans and how it works. However, let me say that in the same way as we don't know much the carbon cycle, in the same way, there are several details of the water cycle that we still don't know. And they are the subject of an active research, very important research. In fact, the science of hydrology, which is the science studying the water cycle, is very popular and flourished in the past more or less 100 years. And it's still increasing. And when we look at the international scientific activities at the global level related to the Earth system, so Earth system sciences, the number of hydrologists is typically larger than the number of people who are working in the other disciplines, because hydrology is still a science that suffers from many unknowns. And let me give you an example. We still don't have an estimate of the volume of water flowing from the continents to the oceans, passing from the continent to the oceans, not through the rivers. So we have a reasonable knowledge of the water flow through the rivers, but we don't know at all a good knowledge of the water flow in the underground, so groundwater, from the land to the ocean. And this is a big miss. It's a big miss because this water from the land to the ocean through groundwater probably is larger. The volume is probably larger than the volume conveyed by the rivers, and therefore it's influencing anyway the movement of the oceanic currents. And the movement of the oceanic currents is a driver of climate. We know the Gulf Stream and many other important currents in the oceans that are influencing El Niño, for instance, the climate, heavily influencing the climate. And these currents are also in turn influenced by the underground flow of water, like the flow of water from rivers. And therefore, not knowing these fluxes and there are several efforts now of global modeling, global water cycle modeling, trying to get a good estimate of these fluxes, but still they are very uncertain. Not knowing these fluxes is something that it's really missing. Just to say that if you are interested, hydrology has the potential for giving important contributions. As you know, I am an hydrologist, so on the one hand, I am a bit biased because, of course, I like what I do. On the other hand, I have a fairly good knowledge, and I can really say what are the important misses. And I think the links between hydrology, so hydrosphere, and the oceanic system, the link, the poor quantification of this link is one of the big questions. But let me look now at another cycle, which is interesting, I believe. It's the energy cycle, energy exchanges. And now we are talking of something that needs also to take into consideration the contribution from the space. It's not only an internal cycle. It's a cycle that needs to take into account the exchange of energy between the Earth system and the planetary system, the space system. This first picture, which I'm showing to you, just shows that the sun heats the Earth system through radiation. We already mentioned it. So when we say solar radiation, something that is watt per square meters, usually it's the unit, something that we can measure with uncertainty, with a lot of uncertainty, but we can measure it. Radiation is giving the influx of energy. And then there are two mechanisms from which the Earth system can exchange energy internally or externally. And these two mechanisms are conduction and convection. What's the difference? Convection is an exchange of energy associated to a flow of matter. Like if I exchange water from the earth, from the lakes, rivers, through evaporation, I exchange water with the atmosphere, there is a flux of water from the land to the atmosphere. And associated to this flux of water, there is an energy exchange. And therefore, this is convection. But there is also conduction, which is exchange of energy, for instance, exchange of heat, between bodies or systems without flow of matter. It's an exchange due to the fact that there is a gradient of energy, a gradient of, for instance, heat. There is a difference in heat, and then there is an exchange of heat, which is an exchange of energy, that is called conduction, which is not related to a movement of a flow of another matter. And let's just keep into account this difference, these definitions, convection, conduction, and radiation, which is simpler. And then let's look at this nice figure, which requires a little bit of discussion, but I think it's very meaningful to clarify what are the most important energy exchanges. And here they are quantified in different colors identifying different exchanges between different bodies. So for instance, if you look at the blue arrows are the exchanges of energy between the sun and the other spheres of the Earth system. And the energy that comes from the sun in a given time frame, you can define, it's not important because here it's not the absolute number that is given of the energy incoming. It's a relative number, which is quantified in 100. So let's define in 100, whatever units, whatever the time scale, the energy from the sun to the Earth system. And if we take 100, then we get a 23, a quantity of 23, so 23%, that is reflected directly by clouds back into the space. And then we have a 19 that is absorbed by the atmosphere. And then we have a 4 that is absorbed by clouds. And then there is a 7 that is reflected by the surface. And then finally we have a 47, which is 100 minus 7 minus 23 minus 19 minus 4, that is absorbed by the surface. Okay, this 47 is absorbed. Okay, fine. Now let's look at the red arrows. The red arrows are related to the exchanges of the atmosphere with the other parts. So basically, we have, first of all, what is the energy that is taken by the atmosphere? Because we don't have the income here in the red arrows. The income has to be searched in the arrows of different colors. So we said that 19% of the energy from the sun is absorbed by atmosphere. So this is an income, 19. 4 is absorbed by clouds. Clouds are in the atmosphere. So 19 plus 4, it makes 23. And then let's see, we have from the land, yellow arrows, latent heat, water vapor changing to liquid or ice. So it's 24 from the land to the atmosphere. So 23 plus 24 is 47. Good. And then we have a sensible heat, 5, and therefore 47 plus 5 is 52. And then we have emission by the surface absorbed by atmosphere is 104. So the total income, if I didn't make any mistake, is 256. So we expect that now the sum sorry, I made a mistake. It's not 200, but it's 104 plus 52. It's 156. Okay. Now I expect that the sum of the red arrows is 156. It's 98 plus 49, which means 147 plus 9, which is 156. So the atmosphere is in balance. So basically from the atmosphere we have emission to the land. It's 98 plus emission to the space, 49, and emissions by clouds to the space, 9. Very good. Now, let's look at the land. For the land, we have 47 coming from the sun, plus 98 emitted by the atmosphere, is 145. 145, yes. Now, the land emits 116, okay? And then the land emits 29 latent heat plus sensible heat. So 29 plus 116 is 147. So also the land is in balance. And if you look, and also it's in balance if you look at the energy that goes back to the space and the energy that is retained by the Earth system, everything should be in balance. And this diagram gives to you an order of magnitude. This is the reason why it is important. So it gives an idea of what is the percentage of energy from the sun that reaches the ground and the percentage that is retained by the Earth system, which is used then to fuel the various cycles. Okay, so it is used in order to also allow the evolution of the different processes. Now, where is climate change? Where is impacting here? It is impacting in the emissions from the Earth system to the sun. It is impacting because the greenhouse effect reduces these emissions. So basically, if you look at the 23 reflected by clouds, if you vary the cloud coverage for human impact, then this quantity increases, and it's estimated to be 23%, and therefore the changes may be significant. Also, they're reflected by the surface, the 7 is influenced by greenhouse gases, and then there is the emission by the atmosphere, 49, which is influenced, and the emission by the clouds, and also the emission from the land directly to space. You may think of something like, but if there is an imbalance, so the energy that comes from the sun is kept by the Earth system in a larger quantity, then temperature should increase forever. Actually, when there is global warming, the temperature of the atmosphere increases. And therefore, under global warming, the emission by the atmosphere, which is proportional to the gradient, because there is no flow, this is conduction, not convection. If you increase the temperature of the atmosphere, then there is an increase of the emission. And therefore, if we just increase the CO2 concentration in the atmosphere, like 10%, what would happen? And then that's it. There is not a continuous increase. If we induce a delta, and that's it, then what happens is that you have an increase of the temperature of the atmosphere, which increases the emissions from the atmosphere to the space until you reach a new equilibrium. In this new equilibrium, however, you have a temperature of the atmosphere that is larger. So this is the way the Earth system reacts. There is an increase of the energy that is stored, a temporary increase of the energy that is stored by the Earth system, which is compensated by an increase of temperature and a corresponding increase of energy that goes back from the Earth system to the space until you reach a new equilibrium. And this is the way the system reacts. If however, the CO2 concentration continues to increase, then there is again an increase of temperature and then an increase of at the reach of a new equilibrium, but still at the expense of an increase in temperature. And this is what we want to avoid. So we want to avoid that we have this continuous increase of temperature if there is a continuous increase of CO2 concentration in the atmosphere. This is why Bill Gates, in an earlier and quite bizarre idea, said, why don't we try to screen the atmosphere in some way, or to protect the Earth, to make it more reflective, so that the direct emissions from the Earth to the atmosphere increase. This was the bizarre idea. This is the field of geoengineering. Geoengineering is the field that tries to study how to engineer the Earth system in order to increase the transfer of energy from the Earth system to the space, therefore lowering the temperature, thus compensating the greenhouse effect. Okay, if you look for geoengineering in Wikipedia or Google in general, or artificial intelligence, whatever, there is a lot of literature. because also carbon storage, artificial carbon storage in the soil is a branch of geoengineering. What is the idea? Just to open this parenthesis. The idea is, okay, humans are taking carbon from fossil fuels and releasing them in the atmospheres. So given that the storage, the deposits of fossil fuels become empty, why don't you use these wells, these oil wells as vectors for injecting atmosphere. So let's say injecting CO2 back in the soil. So let's take CO2 from the atmosphere and let's inject it back into the soil to replace the carbon storage that we used for fossil fuels. And there are a lot of activities in now, especially in the United States, for CO2 storage in the soil, with a lot of uncertainty about that. This is a way to try to accelerate the formation of fossil fuels. So it is a way to react to the exploitation of fossil fuels by rebuilding them through CO2 injection. But this is costly, requires a lot of energy, and also there are doubts about the chances of success. So how long will it take before rebuilding, before reforming fossil fuels? And perhaps more relevant question, what about leakage? Because there are fissures, cracks in the rocks, and there is the possibility that there is a leakage of the CO2 that is injected back through these cracks back to the atmosphere. And there is no way to measure it because it's not possible. So geoengineering is the branch that tries to mitigate climate change by using engineering in this way. It's, it is a very uncertain field. And in fact, the idea of Bill Gates was so far discarded. But still, you may know that in the Alps, they started covering the glaciers during summer with white nylon tissues in order to increase the radiation and limit the melting of the glaciers. This is done especially in the skiing resort, but there were ideas to try to propagate these activities, to expand these activities, these protection measures. Anyway, the graph is important for getting orders of magnitude, and I think it is another useful, helpful way to study the links. Okay, so let's try to look at the dynamics then of the system. And we already know, we discussed already, there are many interrelations. There is a lot of complexity. And I will discuss just now what complexity means to me. Complexity means a lot of equations, a lot of variables. And remember, when you study these cycles, when you study these systems, what is the purpose of the study? The purpose is to describe variables that are unknowns. Variables means important indicators of the state of the Earth system, like temperature. Like temperature in the future climate is an unknown. And these variables in general depend on time, because the Earth system is evolving in time, and we need to evolve to describe the evolution in time. So these variables that are unknown depend on time, and in general, they also depend on space. And the space, keep in mind, that has 3 dimensions. And therefore, these variables depend in general over 4 independent variables. Location, 3 variables, spaces is 3-dimensional, and time. So the independent variables are 4. You know that describing a variable, which means a dependent variable, depending on one independent variable, sometimes is already a task, is a challenge. Can you imagine with 4 independent variables, the complexity? And can you imagine the number of unknowns, the number of variables that are unknowns that we need to describe? Temperature, rainfall, wind velocity, sea level. This is complexity. It means the need to describe several unknown variables which depend on several independent variables. This is complexity. To describe these unknowns, we need inputs, which are input by definition is known, and therefore we need the data, which we already discussed. But there is also a but. When you describe a relationship, a mathematical relationship between an input and an output, let's suppose that the output is one variable that is unknown. Okay? Now, you may need to include additional unknown variables in the description, which means that to describe some unknowns, like the flow of a certain matter, you may need to describe also an intermediate unknown. And let me give you an example, because it's very easy to give an example. Check the Blackboard. So I have to look at my, I have to write here. So let me give you a very simple example to a very simple system, which is a bucket system. Let's suppose that you have a bucket system that originates a flow of matter from the bucket, from the bottom of the bucket, for instance, and you have an input of matter from the top. So let's call this input P. So let's imagine a water bucket. Water is a good example. So you have a water bucket with an hole over the bottom, and then you want to describe the outflow from the bucket. Let's call it Q. And what you need is, and what the input data is the inflow to the bucket. So you may think of something like, okay, let me find a relationship between the input and the output. This is very simple. You can imagine of a lake, for instance, like Lake of Garda, Lago di Garda. You have the inflow from the rivers flowing into the lake, and you have the outflow from the final output. And you want to describe this outflow from the Lago di Garda. Or let's even look to a bucket that can be, you can also take one of your buckets at home. Some of them have a tap at the bottom. You can open the tap and you put the bucket under a water tap. You measure the inflow and you want to describe the outflow. So you have to look for a relationship between the inflow and the outflow. And you may need also the geometry of the bucket, but this is not really necessary. So what is a kind of equation that you may think of? It's conservation of mass. Conservation of mass applies to this scheme. So I want to impose that the mass of water is conserved. Okay. So this means that if I impose conservation of mass and I know the input, then I can write the output. But there is a but. Not all the input is converted into the output, because if I could say that everything that gets into the bucket is transformed into the output, the equation is very simple. Is Qt is equal to 3. This means that everything that gets in gets flown out. This is very simple. And indeed, this is not what happens. Because if you make this experiment with your bucket, you would notice that in the bucket there is accumulation. There might be accumulation of water. And let's call this volume of water stored inside here with the symbol WT. And I have to take into account this accumulation. If there is accumulation, I have to take it into account. What does this mean? That I am introducing an additional variable. If this additional variable is identically 0, then that's fine. I don't need a further description, a further variable. But in general, it is not 0. And therefore, I need also to describe this one. And this is a good example of what I previously mentioned. If I want to describe one variable, generic variable, depending on the input, I need sometimes to introduce additional unknowns. And in general, this happens every time there is a storage. So when there is a storage into a mechanism, maybe I'm not directly interested in it, but I need anyway to model it if I want to be able to model the variables I am interested in. So for instance, in the carbon cycle, there is a lot of storage because it's stored in the oceans, it's stored in the underground. This means that I need to describe also storage. This means that the number of unknowns is increased. So even if I start with only one unknown, it's the outflow from the bucket, I need to introduce another unknown, which means that the conservation of mass is no more enough, because I have two unknowns, I need two equations. So it's not only conservation of mass that gets into play here. I need an additional equation. And what is this additional equation? Every time you have a flow of matter, an additional equation is something related to conservation of energy. But let's not to anticipate too much here. I just wanted to emphasize why there is a complex dynamics. Another reason for complexity, which is the number of equations. The number of equations is very large. And then there are the tipping points, and the tipping points, we already discussed them. We have to translate them in mathematical relationship. And then there is another issue that you have to get very familiar with, which is related to the tipping point. It's non-linearity. So what does it mean, non-linearity? Or why very often we say, even in our common speech, day-to-day speech, we say, oh, this is very linear. It means this is very predictable. It is very simple to understand. But this is a linear reasoning. How many times you said, this is a linear reasoning? And how many times instead we say, oh, this is really non-linear? Maybe less than the times that we say this is linear reasoning. But sometimes, also in the TV, you listen mentioning a non-linear reasoning like something very complicated. So what is linearity then? And what is non-linearity? This is something that you have to become very familiar. I tell you this because when I started as a PhD student, my advisor was giving for granted several concepts, and he said, this process is non-linear, so please take care of it. And I thought, what does this mean, non-linear? I mean, I knew what is a linear equation and what is a non-linear equation. I knew that a straight line is a linear equation, is represented by a linear equation, and I knew that a parabola is governed by a non-linear equation, but I couldn't really figure out in the context of system analysis, system dynamics, nonlinearity. What does this mean? So it means basically that we have the governing equation that is nonlinear. So let's start from a very simple definition. What is a linear equation? And let's look at the blackboard. There are two mathematical conditions. We need to ensure in order to say that an equation is linear. And these two conditions are, first of all, what we call the superposition, I think, not superimposition, or maybe superimposition, I don't remember, principle. In Italian, it's principio di sovrapposizione degli effetti. I think it is superimposition principle. We can check. Okay. And the superimposition principle means that if I have a function of x plus y, the result is given by fx plus fy. This means that if I have two perturbations in a row over a system, the result is given by the sum of the two individual perturbations. Okay. Like, for instance, if I put a finger on the table and with a number I give 2 hits, the amount of pain is given by the sum of the two individual pains of the 2 hits. And this example is an example of something that is not true. So it's nonlinear. Okay. And this is why sometimes we say, okay, if you have to make 2 surgeries, try to make them in one time, because so the pain is just one and it's not twice. Okay? Because we know that the pain doesn't sum. But this is not relevant. This is an example that is not relevant to us. Let me make another example. By referring to a famous proverb, we say something, it rains over the vat. What does it mean, it rains over the vat? It means that it's a problem. It's a nightmare. It's a problem. Why? Because when it rains over the arid soil, over a dry soil, we know that nothing happens. In terms of flooding, for instance, because the soil absorbs. So this means that if the rain is like 10, and the capacity of the soil to absorb water is 15, then I see nothing. It rains and the soil gets it. Very good. Superimposition principle would mean that given that rain of 10 means 0, no problem. And another rain of 10 means 0, no problem. The superimposition principle would say, okay, so F rain of 10 plus 10 is equal to rain over 10 plus rain over 10. So the result would be 0. This is not true because 10 plus 10 means 20. The capacity of the soil to retain water is 15. The result is that I have a 5 of water that is over the soil, not absorbed. So this is why we say it's a trouble if it rains over the wet, because if it rains over the dry, no problem. If it rains over a soil that already got a rain, then we get a flood or we get a trouble anyway. So it means that rainfall and reaction of the soil is nonlinear because there is a threshold which is given by the capacity of the soil to retain water. So the superimposition principle in general for natural processes is not true. And then there is a second condition for ensuring linearity. Means that if you have a function of alpha multiplied by x, this function is given by alpha times the function of x. In graphical terms, linearity means that if you make a graph of x independent variable and fx, the unknown, the graph is a straight line. So anytime that you see a picture, a graph of an unknown depending on independent variable, and the picture is not a straight line, then it's nonlinear. And even if you have something like this, so let's suppose that you have here x and fx. This is a straight line. This means that in this domain here, function is linear. Here it's linear. Now, let's suppose that when I go on the right, I get something like this. Okay, so there is a change of slope. This means that here it's non-linear. Non-linear. This is not a straight line. And if you try to make a check, these two conditions are no more satisfied. This is called, by the way, piecewise linear. It means that it's linear here, it's linear here. So in the individual pieces, it's linear, but when you put them together, it becomes non-linear. So what is the problem with non-linearity? Suppose that, and I hope that we can switch here. So this is like, in this case, this is time for, let's say, again, x, fx. Okay. And let's suppose that our non-linearity is structured in this way. What does this mean? It means that, and this happens in climate science, if I look at this domain here, this is linear, so let me just put it in red. This is linear. And therefore, I may get the feeling that it's relatively easy to make predictions. I can build a model that fits well in this domain, in this orange domain, and then I could make a prediction to extrapolate. And this is my prediction, based on my linear model. This means that if I get an x value that is outside the domain that I observed, I make a prediction that the result is not much different. While the reality is this one, which means that for this value of x, I get a value of fx that goes to infinity, or almost to infinity. And this is concerned. This is a typical case of a threshold effect. Here there is a threshold, which means a change in the dynamics. And this is, for instance, the case of the soil that I made just a few minutes ago. When the soil retention capacity is reached, then the reaction to the rainfall of the soil becomes completely different. Non-linearity is increasing uncertainty and in the prediction. Non-linearity, therefore, is a concept that you have to get very familiar with, and it is strictly related to chaos. What is chaos? Chaos is what is referred to by Lorentz in the example of the butterfly flipping the wing in Japan, causing a tornado in New York. So Lorentz said, look, if you have a nonlinear system, even if you perfectly know the dynamics of the system, it may become difficult to predict. Why? Because a nonlinear system is very sensitive to the initial conditions. So it is very sensitive to the value of the input data. And even a small change in the input data, and he said, a butterfly flipping the wing in Japan, even a small change in the x, like in this graph here, can cause a big change in the result, which is the tornado in New York. So he said, without the butterfly flipping the wings in Japan, you don't get any tornado. You put a butterfly flipping the wing, and you get a tornado. And he proved it mathematically. So what is the result? The result is that even if the system is completely known, completely determined, if you make even a minor mistake in the definition of the input, which is the initial condition, then you get a big change in the output. And given that the input, the data, is never measurable with certainty, because even when we measure temperature, there is uncertainty in the thermometer, this means that the system becomes unpredictable based on the observations, even if it is completely known, because if I introduce a minor change in the input due to measurement uncertainty, like the thermometer, then I get a completely different result, and therefore it makes the system unpredictable, even if it is perfectly known. This is chaos. And remember it, because when you discuss about climate, chaotic behaviors, chaos, it is frequently mentioned. Chaos means that even if we understand everything, and this is not our case, we don't understand everything on climate, but even if we understand everything, still the system is unpredictable. This is why Earth system dynamic is so complex. But at the same time, it is also why it is fascinating. Okay, let's make our break. Let's meet at 3:05. I stop the camera and the micro. Okay, so here we are. We already discussed tipping points, so I'm skipping this slide and also the next one, again, on tipping points. And now let's focus indeed on, more specifically, on the mathematical models. Mathematical models that need to be based on a theory, and the theory in turn is based on our understanding. Mathematical models are needed in order to make predictions and therefore to devise mitigation actions and adaptation actions. So, what kind of models can we use in view of the complexity of the problem, of the complexity of the system? And let's also take into account that models should not only deliver an estimate of the variable of interest, but should also deliver an estimate of uncertainty. Because if we want to design strategies, intervention strategies, we also need to make a cost-benefit analysis. And in order to make a cost-benefit analysis, we have to assess the uncertainty of the benefits and the uncertainty of the costs in order to make sure that indeed the strategy is sustainable. And such assessment of uncertainty of the results means that we have to in turn deliver an assessment of uncertainty for the variables of interest. So if the purpose is to model the future temperature, then we need not only a prediction, what is called also the best prediction, but we also need an assessment of uncertainty. Now, then what kind of models can be used? So there are many possible solutions. It may be helpful to categorize these solutions, to discuss categories, to subdivide solutions into categories. And here you see two first examples of classification. Broadly speaking, we can divide any model into two categories. On the one hand, the process-based models. On the other hand, the empirical models. What is the difference? The difference is that the process-based models are based on the knowledge of the theory. So we first understand the theory, and basing on the theory, we build a relationship between input and output. This is what we call process-based models. And in the case of physics, if the laws that we apply are laws of physics, then we may call the process-based models, we may also call them physically based models. So when you are mentioned a physically based model, it means that it is a model of the Earth system based on the equations of physics. They are frequently mentioned because indeed physics, the laws of physics are an essential component of Earth system models. And in order to give you a first example, we will discuss later more in detail, but the first example is precisely conservation of mass. Conservation of mass is a physical law, is a law of physics. There are also other mechanisms in the Earth system which require additional laws besides physics. For instance, if we talk about ecosystems, then there are evolution equations that very often we need to take into account. So the equations governing the evolution of living species like natural selection and other laws of this kind, and also in empirical models, in process-based models, we may also consider for ecosystems the laws of chemistry, because they may be essential for describing certain types of living organisms. This is a first classification. What is the counterpart of the process-based model? It's the empirical model. The empirical model is a relationship relating the input with the output under the only condition that it works. It is not necessarily based on the underlying theory. It can be, for instance, a regression model, which may completely ignore the underlying theory. The regression model is the same model that we can apply to, for instance, study of global warming and studying the agricultural production. Completely different processes, the same model, because it's empirical. It's not based on the underlying theory. These kind of models, empirical models, were widely used in the past because, first, in the past, and still today to some extent, we didn't have a full knowledge of the theory. And therefore, we needed to make models without the support of the theory. And second, the process-based models, when the system is very complex, are very complex models. Empirical models are, in many cases, simpler. They look at the simpler solution to describe what we want to describe. What is the limitation on the other end of the empirical model? The limitation is that given that it's not based on the knowledge of the theory, it may not work in different conditions with respect to those for which the model has been set up. So, for instance, extrapolation, like the example that I give here for the nonlinear function, extrapolation is frequent in Earth system modeling, which it means that we want to model a future, to predict a future that is working in different conditions with respect to the observations that we have collected. In the future, we will have two CO2 concentration according to certain scenarios, and we don't have observations collected under the two CO2 reality. We only have observations collected in the one CO2, which we, with our models, extrapolate to work in condition 2 per CO2. CO2, which means extrapolation. And then empirical models in extrapolation are running under conditions that they were not trained to, and therefore may be uncertain. The process-based models, based on the knowledge of the theory, in principle, are safer for extrapolation. Another important categorization divides the models in other two categories. And these are the stochastic models and the deterministic models. What is the difference? First, both of them can be empirical or process-based. Don't make the mistake of assuming that statistics is empirical. Stochastic is a synonym of statistics. It's not really a synonym, but let's now treat it as a synonym. So here you read the stochastic model. You could have read a statistical model, and the meaning for now, for us, is the same. Okay? So don't make the mistake to assume that a statistical model is empirical. No, there are some statistical models that are physically based. Think of quantum mechanics. Quantum mechanics is statistics, and it's a physically based model because it uses equations of physics to describe the movement of electrons. And therefore, what is the difference then between stochastic models and deterministic models? I give you the canonical definition. A deterministic model associates to a given input always the same output. Okay, so an equation fx for a given value of x gives always the same value of fx. This is a deterministic model. Okay. A stochastic model is the opposite. For the same input can deliver a different output. Why? because of uncertainty. So the stochastic model takes into account uncertainty in our knowledge, and therefore, any time that you run it, uncertainty means that the result is different. Like if you measure temperature twice in the same day at the same time with two different thermometers, you get two different measurements because there is uncertainty in the measurement of the thermometer. So basically, it is a clear example where same time, same process, same input. It means that the heat in the atmosphere is the same input, different output, because there is uncertainty. So the stochastic model takes this opportunity, this reality into account, and therefore it never delivers the same input for the same output for the same input. Why we are studying these categorizations? Because I want that you get familiar once again with the terminology, and therefore the purpose is that besides learning the concepts, you also learn the terms in order to support the discussion that you may have with your peers, your colleagues. Okay. Very good. Now, let's try to learn more about models. Okay. So this is an example of a deterministic model. This is a figure that I created, which is on the public domain now. So it refers to rainfall as modeling rainfall a long time. So if you have a deterministic model for a given input, you get always the same output, 1-to-1. If you read in the upper panel, 1-to-1 means same, no uncertainty. So in the physically based stochastic model, in principle, in the stochastic model, let's forget physically based for now, you have many-to-many. So you have input with uncertainty, output with uncertainty, and therefore many-to-many relationships under the same model. And this allows assessment of uncertainty. And given that our premise was that uncertainty assessment is important, you understand why the stochastic model may have a role. It is possible to transform a deterministic model into a stochastic version. It is possible. So, in principle, you may conclude, so why not using always a stochastic model? And the reason is that with a stochastic model, based on the definition, you need to run it more than once. And therefore, run it more than once, because in order to get an understanding of uncertainty, if any run gives you a different result, if you want to get an envelope of several results in order to quantify uncertainty, you need to run the model many times, many. And therefore, the computational requirement is larger. And therefore, with climate models, already running a climate model is computationally intensive. Only few research centers in the world, two located here in Bologna, by the way, can run climate model, and at the price of an enormous consumption of energy, release of CO2, etc., then you understand that there is some reluctancy to apply stochastic models in climate science. Still, it is possible, it is not impossible, and we have to know this approach. And keep in mind that what I just said, a deterministic model can be transformed into a stochastic one. So it is not a completely different approach. It is just an added value, the stochastic approach, which requires added computational efforts. And simply speaking, if you need an assessment of uncertainty, then you may consider it. If you just need to know a general pattern of the prediction, so I want to know the most likely value for the future, and I don't care about uncertainty, then why to use a stochastic model? It's not required. If we want to study the reaction of the system to a change, like I increase the CO2 emissions, and I want to see how much is the increase of temperature, I want to understand what is called climate sensitivity. Climate sensitivity is the reaction of given variables like temperature to an increase of CO2. This is climate sensitivity. So I want to study climate sensitivity. Then I think uncertainty may not be needed. I just rely on the best estimate and I say, on the best of my knowledge, there is this kind of reaction of the system to a perturbation, on the best of my knowledge. And then if one asks, and what about uncertainty? It's a different question. Okay, uncertainty, this figure is dedicated to the discussion of what is uncertainty. We already discussed it many times, so let's forget about it, okay? Just beware that there are some applications of climate science where uncertainty is not needed, assessment of uncertainty, other branches where it is needed. In engineering, there are ethical principles suggesting that in any step of engineering design, uncertainty is to be carefully evaluated. What is the problem in climate science? The problem is that uncertainty sometimes is so relevant that assessing it may lead to including no change into the range of uncertainty. Let me explain better. If I want to study the increase of temperature due to twice CO2 concentration, and I use the models that are available for that, and I compute uncertainty, it may come out that in the range of the uncertainty, there is also the condition, no change of temperature. This is problematic because when you speak with a policymaker or an administrator, you may say, okay, if we keep the business as usual scenario, temperature may increase by 2050, 0.5 more degrees, but I am not sure, may also be that it doesn't increase at all. Okay, this is something that in a relationship with a policymaker makes the relationship very complicated, because then the policymaker may require, okay, that's fine, but what is the probability of getting a change? And this goes beyond uncertainty assessment. It's a very refined uncertainty assessment. And we don't have the computational means today for making such a detailed computation. And therefore, it becomes complicated. This is why uncertainty in climate science is a word that sometimes provokes a kind of this kind of reaction. I don't know how to say in English, blinking the eyes like, okay. Okay, now, what is the purpose of a model? Is to describe the effect of a perturbation, okay? And therefore, this may need extrapolation. And what I am discussing in this slide is that extrapolation, to some extent, is something that it's unavoidable because the Earth system is never in equilibrium. So we live under the perception that without humans, the Earth system would be perfect. No perturbation, no floods, no droughts, and no changes. Actually, if we look at the history of Earth, at the history of the Earth system, we realize that even without humans, there have been perturbations originated by natural causes, and there have been changes, and the Earth system has been continuously changing. It's never in equilibrium. It remains in a state of fair equilibrium, first of all, more in the past 11,000 years. And this is why prosperity increased, because in the past 11,000 years, according to the information that we have collected with proxy data, the climate has been more stable than in the previous history. Still, 11,000 years is very short, so it may change the situation. But this is why the human prosperity increased, because it's a stable situation. It's a stable situation that gives like the feeling that everything is in equilibrium without humans. Actually, the situation remains fairly stable even with the humans, and it is something that is continuously evolving. So extrapolation is, in a way, unavoidable. And even without the 2CO2 scenarios, on the other hand, the question remains on how to make sure that our models work, but even the models that we used before climate change, we used to make predictions. We used to make prediction of economic predictions and Earth system predictions of any kind. And we were used to apply specific models, and even these models were subjected to this problem of extrapolation. And however, we need to take into account that there is also this additional question. So when we set up our equations, how to make sure that extrapolation is leading to meaningful results. And therefore, one first conclusion is be careful with a full empirical model, because a full empirical model has already demonstrated that sometimes we made big mistakes. So let's maybe stick on the laws of physics, or in any case, let's stick on the theory, on process-based models. And if we want to estimate uncertainty, let's consider the stochastic opportunity. We are discussing issues that are leading us towards defining the structure of models. This is a slide that I included for making opening and closing a parenthesis in order also to breathe a little bit. This figure shows an analysis of changes that occurred in the magnetic field. And I would like also to mention this phenomenon, the magnetic field, which is related to the movement of iron in the core of the Earth. So it is originated, the magnetic field is very important because it creates like a screen against the solar radiation. And it's very important because otherwise the direct exposure of the living systems to solar radiation would be really dangerous, really threatening the survival of life. The magnetic field is creating a screen. And it's, as I said, it's given by the movement of iron in the core of the Earth. And it has a pole, a positive pole at the north and a negative pole at the south. We know that in the history of Earth, the magnetic field underwent sudden inversions of the pole, sudden, in the time span of, on a limited time span, it inverted. And this occurs with a frequency on average of, I don't remember really if you check, but several hundreds of years. And there is this inversion of the poles, which is, we try to predict, but it's impossible to predict. And will have an impact on, not really a shocking impact on humans, but it will have an impact also on climate and also on our life, because it's not very clear what could happen also to our health when the magnetic field is inverted. And we can check, because I don't remember, and I want to give you an idea of the frequency. So inversion, magnetic field, geomagnetic reversal. Oops. Okay. A geomagnetic reversal is a change in the Earth dipole magnetic field such that the positions of magnetic north and magnetic south are interchanged. The Earth magnetic field has alternated between periods of normal polarity and reverse polarity. Reversal occurrences appear to be statistically random. There have been at least 183 reversals over the last 83 million years. So on average, once every 450,000 years. Okay, and the latest, the Bruns-Matuyama reversal, occurred 700,000 years ago. So a long time ago. Okay, and the duration of the reversal is about 7,000 years. Actually, it's not so short. The timing I remembered short, but it's short in geologic times. Actually, it takes a long time, but of course, during the transition, there are impacts of changes. So I am fascinated by these things that we don't really know in detail. I am also fascinated because I talked along with scientists dealing with these issues, because I try to understand what could be the influence on climate. There is for sure an influence of on climate. And you see that these scientists are predicting that, basing on the average frequency, it could happen quite soon, another geomagnetic reversal, which may take thousands of years to occur. And so it's something that has a different time scale with respect to our climate concerns, but still, it's something fascinating. Okay, let's move forward. Now, sorry, this is duplicated. Okay, now I have to go because the PowerPoint is concluded, but not the lecture. So let me close here and let's go here. Very good. No linearity, we talked about it. Process-based, deterministic versus stochastic. Here there is a full description. And now, mathematical structure of models. This is what I want to discuss in 10 minutes now, and we will move forward next week. So first of all, let's be aware of the meaning of input variables, output variables, or unknown, and state variables. Therefore, state variables in general are unknown. So if we think of a model, of an Earth system model, and maybe a model of the whole Earth system, or a model of only a given subsystem like hydrosphere or climate system, etc. These models are anyway systems of equations, and we concluded that it's better if these equations are physically based. The number of equations is at least equivalent to the number of unknowns. Therefore, we need to first assess what are the unknowns, how many are the unknowns, and what kind of unknowns. So we have to identify the output unknown variables. In general, all the outputs are unknown, and the type of unknown state variables. Now, what are the equations that we can use? The number of equations equivalent, as I said, at least the number of unknowns. The equations of physics are the first candidates, in particular if the unknowns are physical variables. And ideal candidates for these equations that in general describe the transport of matter and energy exchanges and related energy exchanges, the ideal candidates are conservation equations. what are conservation equations. We already made a first example with conservation of mass. And here there is a link, let's explore it. Conservation of mass. So, in physics and chemistry, the law of conservation of mass, or principle of mass conservation, states that for any system which is closed, and this is our case, closed to all incoming and outgoing transfers of matter, the mass of the system must remain constant over time. Okay, mass of the system, of course, the mass of the relevant quantity. So in the case of the bucket, is the mass of water, but it can be the mass of carbon, can be also energy, which is not a matter, it's energy, but I can apply conservation of energy. In general, if the system is not closed, I can anyway apply a conservation principle by including as additional terms income and outcome. So in the case of the bucket is not closed. It receives an input PT of water and there is an output. What I applied is a conservation of mass because I accounted for the contribution of this input and output. When the system is not closed, you may also use the term balance equation, which is equivalent. But conservation, indeed, according to some interpretations, implies closeness of the system, while balance doesn't imply closeness of the system. For our purposes, for my purposes, I always treated conservation and balance in a imprecise way as synonyms. Okay, so in chemical reactions, for instance, the mass of the chemical components before the reaction, I'm reading here, is equal to the mass of the component after the reaction. And if there is a decay, we can account for it. So don't interpret conservation as a strict conservation, like the term suggests, and this is why some people are rigorous in that. You can apply conservation of energy even if there are energy losses, provided you take into account energy losses. And then, as I said, some people call them balance equation rather than conservation equation. And this is mass conservation, but I mean, mass is not the only matter that we can conserve. There is conservation of energy and conservation of momentum. Conservation of momentum is the general principle for applying, for taking into account also conservation of energy. Momentum is what in Italian is called quantità di moto, which is mass times velocity. And momentum is a vector, remember, because velocity is a vector. And therefore, it's a vector. And so conservation of momentum implies a larger interpretation, that a wider perspective with respect to conservation of energy, which is a scalar. Energy is a scalar, so it doesn't take into account the direction of the flow. And therefore, we understand conservation of momentum, which under some conditions, under given condition, is equivalent to conservation of energy, in particular for one-dimensional flow. But when the velocity has three components, for instance, and then it means that when the velocity is not a unique, is not monodimensional, is not only a unique direction, then momentum is a wider perspective, implying conservation of energy under certain conditions. This is why here, with the bucket, I anticipated. we have one additional unknown. What can we consider here? And I said conservation of energy, because we don't need conservation of momentum here, because I am interested in describing the flow, which is a scalar quantity. I'm not interested in describing the direction of the flow. If I were interested in estimating the outflow from the bucket and the direction of the flow, then I would need conservation of momentum, because momentum is a conservation of a vector and therefore describes the direction. In this case of the bucket, is conservation of energy. Okay. By the way, I am giving a lot of details, not really for preparing you for the exam. I will not go with the quizzes, and we will make available some tests before the exam, some examples. We will not go into the tiny details of what I'm saying, but as I said, preparing for the exam is not only your purpose, especially because you are surviving here attending lectures in person, which means that you are interested. Okay, so I'm giving these details because I think you also need to get into a mindset and knowing terminology, etc. So this, and also keep in mind the basic laws of physics describing the movement of bodies, Newton laws, okay, which I want to, sorry, I should have linked the direct link to the laws. Just 1 second, Newton. Okay, these are the 3 Newton laws. And remember them because, again, mindset. A body remains at rest or in motion at a constant speed in a straight line unless it is acted upon by a forcing. At any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalently, the rate at which the body's momentum is changing with time. So you see that Newton laws are the basis for the conservation of momentum. If 2 bodies exert forces on each other, these forces have the same magnitude but opposite directions. So remember the Newton laws. Again, not for the exam, even if maybe that at the quiz you find something like very easy about the Newton laws, but remember, because it is really the foundation, these are really the foundations for describing the Earth system. And by the way, this guy here, Isaac Newton, was indeed gave indeed very meaningful contribution to set up the basis of science. And he was a mathematician, but of course he also gave, above all gave important contribution in physics. Okay, I think we can stop here, and then we will go into further details about modeling next time. Thank you very much, and don't forget, if you have questions, to step forward anytime, also by email if you like. Thank you. Bye-bye.